So today is all about trying to find how different rates of change are related. So we call it related rates. The hardest part you'll find in this unit is making the original relationship together. So let me start with an example here where I give it to you. And that's if I have one of those paper cups, that looks like a cone. And the radius is 3 centimeters and the height is 8 centimeters. So if I want to relate the rate and the height to its volume, here's a relationship to do that. So it's not important that you have this specific relationship, but this is the goal that we're going to be doing with everything today is we have to relate everybody with a formula. So let's figure out how the rate of change in volume is related to the other pieces. So we do that implicitly. If I take the derivative of v, that's just dv dt, and now I have to take the derivative of the other side as well, so it'll be 2 pi over 3r dr dt plus pi over 3r squared dh dt. And just to clarify again, here's one of my derivatives, so I'll call this like, this was when I did pi over 3r squared, and this is the one that came from the h, when I have my two pieces here and there. So again, it's the same rules you already know, and it's the implicit differentiation. However, this time we're doing it with respect to time. So this notation, remember, it means the change in volume with respect to time. So if I wanted to explain how the volume is changing, this is the formula to tell me what's happening at any instant. All I have to know is what's the rate of change in the radius and what's the rate of change in the height. So you'll get problems where maybe you're looking for how fast the water is falling, meaning what's the rate of change in the height with respect to time. We just have to rearrange the equation. But let's try and fill it in here. If you were told that the rate of change in the height is negative 0.2 feet per second and the radius is negative 0.1 feet per second, what's the volume at that instant? Well, the change in volume is going to be 2 pi over 3. I know the radius is 8 centimeters, so I need that in order to solve this problem. So that's going to be 3 where r was. And the change in the radius, dr dt, is negative 0.1. Oh, I'm sorry, I forgot an h in there. Just sneak it in there. And so there should have been an 8 there. Originally in the formula here, I forgot the h that was part of the dv dt. My apologies. So this is pi over 3. The radius, again, is 3. And the change in height is negative 0.2. So now it'll be up to my calculator to help me figure out what that would be. So 2 pi over 3 times 3 times negative 0.1 times the height, which is 8, plus pi over 3, and 3 squared, I'll just put it in as 9, times negative 0.2. So overall, let's just take a minute before I hit equals. What's happening to the height if I know the rate of change is negative 0.2? What's happening to the height? It's going down. If you're picturing the water funneling out of the cup, the height is dropping, okay? So what should naturally be the result? If the height's falling, what do you think's happening to the radius? It's also shrinking. Yeah, it should be negative like we were told. And if both of them, they're shrinking, what's happening to the volume? Yeah, we should get a negative answer here, or we've made a mistake, right? The volume should be, we should be losing it. So at that instant, we're losing that much in the volume, so negative 6.91. And what units would we be working in here? Very close. This is volume. Yeah. So the volume units are in feet cubed. Oh, and the time is in seconds. So the change in volume with respect to time, the units would be in feet cubed per second. Now this is not necessarily the strategy you're going to employ, but it's a pretty good one. So I pasted it into your notes for you. You maybe just want to put a star beside it. While you're getting used to related rates, it's kind of helpful if you have some sort of guidelines. So these guidelines will help you if you're getting stuck. However, the most important thing where people struggle tends to be coming up with that equation. So we'll walk through a couple together and see what I'm talking about here as far as making up the relationship. Okay. So how rapidly will the fluid level inside a tank drop if we're pumping out 3,000 liters per minute? So what we want to know, if we read this and we could not see this picture, today I'm giving you pictures. Tomorrow we're going to draw our own pictures and practice this, but today we're just going to kind of see how related rates work in a little bit easier of a fashion, but let's get in the habit. How rapidly will the fluid inside the tank drop? So if we're wanting to know, this is a change in fluid. Sorry, change in fluid level. So the first thing we would do if we didn't have a picture is we would say, I need to find the change in height. That's what I'm looking for. As ridiculous as it sounds, you're going to see quite quickly, as soon as I take the picture away, probably the first thing that people can't figure out is, what am I supposed to find? So look in the problem, and what is it I'm looking for? And you'll notice here, it actually says, write down what you're asked to find. So as I read that, I'm a little more trained at it, obviously. So my first thought is, okay, I'm looking for the change in height. And when I read it's being pumped out at a rate of 3,000 liters per minute, then what we should be thinking about is, okay, this represents the change in volume with respect to time. And it's going to be negative 3,000 because I'm pumping the water out. It does not say that it's negative because it tells you it's pumping it out. You're losing volume. Okay. Now, here's the question. How do I relate? I need some things like the height. I need the volume. And it's a cylindrical tank. Oops, that should have been a comma. I'm going to need a radius as well. So how do I connect these things together? The volume here, this part?
No, the bottom part, like dt over dt. dV over dt.
Yeah.
That states that we're losing 3,000 liters
Yeah.
per minute, right? So we have to figure out, that means dropping by how many on the cylinder left thing.
That's just talking about the volume, though. It's not going to tell us anything about the height, unfortunately.
We're finding the height.
No, hang on. So right now, all I'm trying to do is connect these things together. So does anybody remember?
Cylinder equation?
Yeah. So volume for a cylinder? Yeah. Pi r squared h. So all I want you to try at this point on your own is see if you can take the derivative and do it implicitly. So everyone is with respect to time. Okay, see if you can manage the derivative on your own. Okay, so I almost did it again. I almost forgot the height, but luckily I remembered. So, did I forget something else?
We can't see it.
Oh yeah, I froze it on you. Sorry. There. Is that better? Okay. So you didn't even know I made a mistake. I shouldn't open my mouth. There you go. Yeah, what's up?
Is it H?
Is what?
No, actually, never mind. Sorry.
It's okay.
That was
So, so these are the rates of change in my problem. This is the one I'm looking for here. So what I need to do is I need to solve this equation for the change in height with respect to time. Okay, so try doing that. Move everything so that you can tell me the change in height equals. Uh, is it? Yeah, I think I moved it to the other side, but I flipped it around too. I don't know why, but it just feels better when the unknown is on the left. It always feels weird when it's on the right. So, anyway, now we have a bit of a problem at this point because you look at this and you think, ooh, well, I've got a formula, but I don't know some of the pieces here. So, the volume they told us, this one I know. However, I don't know anything about the radius. Yeah, and there should be an H in there, right? So there's some pieces missing, but one of them we know. Just you have to think about it. Is there a piece there that you know that they didn't explicitly state? Well, you have to think. Well, pi we know it's there. It's pi. Think about this moving. Good. Yeah, say it. It's 0. Yeah, shout it out. How come? Yeah, if you picture that water level dropping, the radius is not moving. It's not going in or out. So the dr dt, we know it's 0. So that piece is gone. That would mean the change in height is unaffected by the radius. It's only the volume, and that should make some sense, right? It's not going to affect our problem here because the radius is a constant. So we can just work with this. Now, there apparently is a little piece of the problem missing. Yeah, so we'll just sneak it in here. We'll say that the radius is 10. Well, for this question we'll do it, yeah. Okay, so we'll sneak in a radius of 10 because I guess I forgot to put it in. If it was a test, of course, you'd have the information there somewhere in your problem. So this will be, looks like negative 30 over pi. I'll get 100, and 100 times 30 is 3. Okay, yeah, so that should work. So this would be negative 30 over pi liters cubed per... Oh, no, sorry, liters is volume. Liters per minute. No, that's the volume. Come on, Mr. Joyce, wake up. Height here, we'll just call it, I don't know. If it was in liters, it's likely in meters per minute here then. So we'll say the radius is 10 meters. That's a big tank. Okay, I'll have to make an edit there. My apologies, but that one got away from me. We should have had a 10 for radius. A hot air balloon this time. So it says a hot air balloon is rising straight up from a field, is tracked by a rangefinder 500 feet from the liftoff point. So already, if I didn't have the picture in front of me, I would need to draw a picture. When you're working with a word problem, if you don't already do this, every time you read a piece of information, it should make its way into your picture. Because whether it's a whole sentence or part of a sentence, it's easier for you to think about if you keep breaking it into small chunks. If you try and do the whole picture by reading the whole paragraph, that's too hard for you to think about. So if I'm reading a hot air balloon is rising straight up, then I would draw this picture here, a balloon going straight up. It says it's being tracked by someone 500 feet away from a liftoff point, so that would be my 500 feet. Then it says, at that moment, the angle of elevation is pi over 4. So pi over 4 should go in my picture. And it tells me that the balloon, the rate of increase is 0.14 radians per minute. Should it be positive or negative if you think about this? That angle should be getting bigger, right? The more the balloon rises. So we should expect that that rate of change is positive, like they gave it to us. The reason I'm telling this to you is because sometimes you have to make those judgment calls yourself. It doesn't always give you that it's positive or negative. You should get in the habit of thinking about whether it's getting bigger or smaller. So that's the rate of change in the angle, so it should go onto our page as well. How fast is the balloon rising? So what I'm looking for, if I want to know how fast is it rising, is I want the change in height. So you could call it dh dt, or in this case they're calling it y, like a y coordinate. Okay. So here's your challenge, because today I said you don't have to worry about these initial steps. All you have to worry about is relating the stuff together. So how could you relate? If this is all everything went perfectly, you've got your picture there, how would you relate the stuff? Pythagoras, okay. Pythagoras would make sense. You got a right triangle there, 1, 2, 3. Is that what I'm trying to capture in this problem? What's wrong with, and it's important that we all be aware, because that might be you too. Why is Pythagoras not the one that I want to do here? There's a key thing. There's an angle, and we're not interested in the hypotenuse. So that's how I know it's not the right relationship, because I don't want this one. I want this one here. What can get me those three? Well, we might run into a special triangle here, but it's just the SOHCAHTOA, right? So which one is it out of SOHCAHTOA? Tangent, yeah, opposite and adjacent. It's funny how those grade 8, 9 skills that kind of sneak away from you after all those years. But I'm going to be saying this. You're making me do it. The tangent of theta is the opposite over the adjacent. Okay? So that means y equals 500 tangent of theta. This is the relationship between the angle and how fast that balloon is rising. So you go and find the derivative now. We're there then, I hope? So dy with respect to time. So 500 is just my constant, secant squared theta d theta dt. Oh, yeah, remember, the variables don't match in a related rates problem because the relationship does not have time in there. When you write this and you ask a grade 10 student doing SOHCAHTOA, find the relationship with time, they're going to look at you like, what? There's no time here. This is y and an angle. So you have to do the same when you do your differentiation. The variables don't agree. You need to have the d theta dt there, like an implicit differentiation. So here I can put in, I know all those values, 500 secant squared pi over 4. And the rate of change is 0.14. So we have 500 times 1 over cosine pi over 4 all squared. Be careful about how you put it into your calculator. I'm going to want to double check this myself. So that's secant pi over 4, that's all squared. Okay, so it looks okay to me. which means it's 140 yes, 140 feet, and we are working in minutes, feet per minute. That's pretty fast if you're moving 140 feet per minute. I don't know if that's practical. Well, maybe, but I think, what's the speed of sound, physics people?
300 something.
300 something feet per second? Okay.
Meter.
Oh, meters. Okay. Even still, that's like about, what, 1,000 feet per second? Well, okay, maybe they're going, I don't know. Anyways, it's not important if it's realistic or not, but this is how, according to what we've been told, the super balloon is rising 140 feet per second at that point. Per minute. Sorry, per minute. Oh, that's why it's per minute, it's not per second. Okay. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and moving east. And it tells us the police, when the cruiser is 0.6 miles north and the car is 0.8 east, they determine the distance. The police determine that with radar, the distance between them is changing 20 miles per hour. So like at this point, we've gone way too far. If we were to do this without a picture, we would have to have start labeling. So right away, what I would have had is, there's a cruiser 0.6 kilometers north, so I would have gone like this. Here's my police cruiser, 0.6. And it says I'm moving east now, and 0.8. Then it says, it tells me the distance between them, here's the distance between them, is going to be changing at a rate of 20 miles per hour. So that's what they have here. Not sure why they used s as the variable, but anyways, ds dt, the rate of change in this is 20. So how could we formulate, based on this picture we've been given, how can you get a relationship going between all these pieces? Where according to this, that's y, that's x, and that's s. Yeah, I've heard it whispered. What's the relationship? Yeah, it's Pythagoras. X squared plus y squared is, and in our problem it's s squared. Okay. So if I take the derivative implicitly, 2x dx dt plus 2y dy dt is 2s ds dt. And what I'm interested in is, what is the speed of the car? So the speed of the car is, according to this model, that's the speed of the car I'm interested in, right? That I want to know how fast the car is going. So that's what I'm going to rearrange and solve for. And I'm about to do some division. That 2 is going to be knocked out of everybody. So let's move the x underneath. And I'll get dx dt. And remember, that represents the speed of this car here. Is going to be s ds dt minus y dy dt all over x. Now all I need to do is use the values I've been given to substitute. I know that y is 0.6. I know that the speed of the car here is 20. However, I don't know this value. Anybody have any bright ideas? Yeah. Good. So we already have the relationship there. But the funny thing about the way your brain works is, now that you're used to all the complicated math, sometimes the easy math sneaks by on you. So the missing side here using Pythagoras is going to be 0.6 squared plus 0.8 squared. I believe it's going to end up being 1, but I should double check it. Yeah, okay, so it's 1. Okay, so s is 1. We know the change is 20 miles per hour. And again, does this go in our problem as positive or negative? Positive. We're told that it's increasing. And if you picture this happening, you're picturing, is the distance between them getting larger or not? So in our case, they told us it's increasing, so it should be positive 20. But there might be a time when it just says the car is traveling 20 miles per hour, or the distance is 20 miles per hour, changing at 20 miles per hour. You'd have to make that decision. So it's positive. We know that y is 0.6, and yeah, they're going 60 miles per hour. There's a perfect example of what we need, needing to make that decision. If their cruiser is going 60 miles per hour, why is it negative 60 miles per hour? This right here represents what y is, and that value is shrinking. So as it shrinks, it's got to be negative then in the rate of change. So this was given to us in the picture today, but we're going to need to make those kind of decisions on our own eventually. So this will be negative 60, and the value for x is 0.8. Okay, so 20 plus 0.6 times 60, and we'll divide it by 0.8. 70 miles an hour. So I've always wondered this one myself, because I'm not sure exactly how accurate the radar guns work, but I kind of assume that you have to be exactly straight on to get the right speed, because as you can see from this, when you point the radar gun, it is going to measure how this angle is changing. So I think that's why you get some leeway. Like, it's very rare that you hear someone say, oh, I was going 51 and a 50 and I got a ticket, right? Usually the police aren't going to try to argue that. But if they're close enough in their accuracy, right, they're going to say, yeah, you deserve a ticket when you were going, 60 and a 50. But I'm not saying you're going to get away with it, but usually there's some leeway in there. Yeah, usually it's about 10. Yeah. Yeah, that's for sure. As long as the guy beside you is going faster. Okay, yeah. Okay, so the last question is, it's pretty common in as far as trying to, see what you can do with related rates. So this one we have to talk about together, but hopefully you'll recognize the conical tank. So a conical tank is just a cone, fancy way of saying a cone. But the reason it's important, you're going to find out real quick when we draw this picture and look at our relationship. So let's start, and you'll see why it's here. So first of all, as soon as we hear the water runs into a tank at a rate of 9 cubic feet per minute, you should immediately say, what does that information mean to us in this problem? More water. So in terms of calculus speak, what would it be? Increasing? What's increasing? Water, which represents volume. Volume is increasing. So in terms of calculus, dV dt equals 9 cubic feet per minute. So, oh, it's already on there. That's this one right here. dV dt is 9 cubic feet per minute. The tank stands down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when it's 6 feet deep? So in my picture, it's a 6 here. All right. Anybody remember from where we start? Well, of course, you have the page right in front of you. So what's the relationship here? Yeah. So the volume would be pi over 3r squared h for a conical tank. I would say there's like a 50-50 shot that you're going to get the formulas when you're working with volume. Some formulas they expect you to know, like Pythagoras and other things. But like volume of a sphere, volume of a cylinder, some of the more common geometric shapes, they don't always give you the volume. So you'll see as we practice, sometimes it's there, sometimes it's not. But this one, I hope it's there. It's not the most common shape. So now let's take a look and survey what we have here. one thing we haven't mentioned in the list of techniques, let's go take a look here. Is to name the variables and constants. So one strategy when you look at, before you're about to differentiate, it's a good idea to see if what you're about to differentiate makes sense. We did this one right here earlier, and remember we found out later, oh yeah, look at this, we didn't need to do all that. We didn't need to do all of that because it canceled out. Well, if I was to survey that formula and pretend that the radius is going to be constant throughout this whole problem, that means this here is a constant which requires no differentiation, right? Derivative of a constant times a function is just the constant times the derivative of the function. So I could have gone right to dv dt equals pi r squared dh dt if I would have thought about it first and said, there is no change in the radius, it's not a variable. I don't know what it is, but it's constant. So this problem could have been simplified if we did that. If I take a survey at the one we're doing right now, it tells me here that when I find this derivative, I'm going to need to know the radius, the height, and I'm also going to need a dr dt, because that is something that's changing. I'm also going to need a dh dt, and I'm also going to have a dv dt. So if I do a quick survey, do I have enough information right now to solve this problem? What am I missing? Or maybe we should start with, what do I have? Let's go through and take, what do I know in this problem? Okay, they gave me the radius. That's this big one here, I think you're talking about? Okay, that's the radius of the entire tank, though. The water level's down here, right? So our problem is that spot. So they've actually not explicitly given us the radius. Could we find it?
Yes.
We could, because we could use this, right, I know this height is 6. I could figure out this one here, but those won't be my problem, okay? Do I know how fast the dh dt is going to be, this change in height? This is what we're looking for, right? We don't know it. We know what the volume is. What about dr dt? Do I know how fast the radius is changing? I don't know that one either. So you're not going to be able to solve this equation the way it is because you have two unknowns in a single equation. So that's why this one's in here, is to show you probably the most common one that you have to be creative about, which means I'm going to use this relationship of similar triangles. If you look at this red triangle compared to, let's say, this blue triangle, I can come up with a way of describing the radius, or sorry, in this case the height, because that's what I want, is I want to know the height. So if I call this, I'm going to stick with radius and height. So this would be h and this would be r. The radius divided by the height is equal to 5 divided by 10. Because of those similar triangles, the radius is to 5 as the height is to 10. That means I can rearrange this problem and say the radius is just half of whatever the height is. So now I don't have to worry about the radius. I'm going to remove it from the problem here. This is going to become that. So now I get volume is pi over 3 h over 2 squared h. That just removed any product rule I'd have to worry about also, so that's kind of nice. So this is going to be h squared over 4 times h. So volume is pi over 12 h cubed. So the cone problem is nice because that investment here of using that relationship has greatly simplified the rest of the work we're going to have to do. The change in volume with respect to time is just going to be 3 times pi over 12 will be pi over 4, h squared dh dt. And since I'm trying to figure out what is the change in height, dh dt is the change in volume with respect to time divided by pi over 4 h squared. I know what the height is, I know what the change in volume is, and pi over 4 is a constant, so I'm ready to put my numbers in and solve. This water is being pumped in, the water level is rising, so I should expect a positive or negative answer. Good. The volume is positive, it's going in at 9, and this will be 6 squared. So I suppose I could try and simplify this here. That 4 is going to get multiplied up, so I'll have 36 over pi times 36. So that'll just be 1 over pi. And since we're dealing with feet and minutes, this would be 1 over pi feet per minute.